Hello students, welcome to today's lecture on artificial neural network. In our earlier class, we have discussed about what is meant by pattern separability, and also uh, we have seen two important topics with respect to the radial basis function neural network. One is Cover's theorem, and the other one is interpolation problem. Okay, so with the basics that we learned in our previous class, today we will continue with the actual topic of this fifth unit, that is RBF neural networks, that is radial basis function neural networks. Today we will see the general architecture of a radial basis function neural network, and also we will go through a simple example that explains about the design of RBF neural networks today. Okay, so let us start our session today. Okay. So look at this diagram. Architecture of radial basis function neural network. Generally, any radial basis function neural network will consist of one input layer, one hidden layer, and one output layer with a single neuron. This I explained in the previous class also. The radial basis function neural network consists of one input layer, one hidden layer, and one output layer with single neuron in it. Okay, and generally, uh, assuming that x1, x2, so on xn as input space, conversion from input space to hidden space is done with the help of non-linear mapping. That is, we will take the help of a special activation function called as RBF function, radial basis function. And then from hidden space to output, the conversion is going to be a linear mapping. That is, we will consider a general activation function that maps the corresponding uh, hidden space into output space. Okay, and the output layer, because it contains a single neuron, it will use a normal activation function finally to produce the actual output of radial basis function neural network. Okay, so the points that you need to understand here is the conversion of input space to hidden space is done with the help of a special function called as radial basis function. We'll see that in a while. And then once the input space is converted into hidden space, we can linearly map the corresponding hidden space into output space, just like we did it in perceptron neural network. Okay, now let us explain this. Let us understand this in detail. You can see it here. RBF neural network contains three layers: input layer, hidden layer, and output layer. As I told, the transformation from input layer to hidden layer is non-linear mapping, and the transformation from hidden layer to output layer is a linear mapping. Okay, so non-linear mapping from input space to hidden space is done by using the radial basis function, as I explained earlier. This is the special activation function we use for mapping our input space into hidden space. Okay, and then the linear mapping is used from converting hidden space into output space. This is generally done with the help of a weighted linear combination of its inputs. That is generally going to be sum of products of weights and inputs. Okay, so it's a general process in neural network, but the speciality of radial basis function neural networks is converting that input space to hidden space from a low dimensional space to high dimensional space. That is what the actual specialty lies in radial basis function neural networks. Okay, then the radial basis function networks are generally used for function approximation problems. That means we will identify a function that maps the given inputs to the corresponding desired responses. Okay, in identifying that function, what we do is we perform two mappings uh, while converting from input space to the final target. Uh, so basically, the RBF neural networks are best suited for function approximation problems where we identify a function f of x that maps the input x to a particular desired response di. Okay. Therefore, what we can say is learning in RBF neural networks can be implemented as a curve fitting problem. Okay, not as a line fitting problem. So it's a curve fitting problem that is done in high dimensional space. So we will not perform any fitting in low dimensional space directly. What we do is we convert the low dimensional space into a high dimensional space first, and then we will solve it as a curve fitting problem. Okay, the curve fitting problem solves it either as a linear separable or curve shape or quadratic shape as I explained in earlier class. Okay, so every radial basis function neural network can be assumed as a function approximation problem. Okay, so that is what the introduction to your architecture of radial basis function neural network is. It generally contains three layers as I described in the previous diagram: input layer, hidden layer, and output layer, where output layer contains a single neuron in it. Okay. Now, let us understand how the radial basis function neural networks can be designed and trained to identify the mapping between input space and output space. Okay. So we will discuss about this with the help of an example first, and then later we will write the algorithm that will be used for training of a radial basis function neural network. So for understanding the process of this RBFNN design, we will consider the example that we took in our previous class, that is XR problem, that is XR gate. The behavior of XR function need to be simulated here. We know that the input patterns for XR is going to be 1 1 1 0 0 1 and 0 0. These four comes as input patterns, and the corresponding desired response is 0 is for two input patterns, that is 0 0 and 1 1. For these two we have an output desired response 0, whereas 1 0 and 0 1 produces 1. Therefore these two comes under the class uh, 1 as desired response. So there are two types of outputs that must be produced by your RBF neural network, 0 and 1. Whenever I give the input 1 1 or 0 0 as input to the neural network, it should produce 0 as output. Okay. Similarly, whenever I give 1 0 or 0 1 as input pattern to the neural network, it should produce 1 as output. Okay. So we want to simulate this behavior of XR function uh, with the help of a RBF neural network, right? Now let us see how it can be done. The first thing we need to do is we need to assume any architecture for the RBF neural network, and the rule is it should contain three layers: one input layer, one hidden layer, and one output layer with a single neuron. Okay, so you can have any number of neurons in the input layer. It is generally going to be depending on the size of the input pattern, and then you can have any number of hidden neurons in your hidden layer. This is your choice. You can use any number of hidden neurons, but generally this depends on the number of classes that RBF neural network is going to identify. So in our example, how many classes are there? As I explained in XR problem, there are two classes of outputs. So one is 0 and the other one is 1. So we will take two neurons here in hidden layer. Okay. So this depending on the number of classes to identify, this depending on the number of number of uh, values in the input pattern. Because we have two values in each input pattern, we will take two input neurons here, and it is always going to be one output neuron. Okay, so this is our first step. You need to identify the architecture of RBF neural network properly in order to proceed further. Okay, so here it is. The number of hidden neurons in the network is assumed to be 2. Why is so? Because the classes that we want to identify is 2. Therefore, generally it will be 2, but you can pick any number for this hidden layer. Okay, so once you select the number of neurons in hidden layer, what you need to do is you need to use the same number of radial basis functions for the hidden neurons. That means if you have two hidden neurons, then you must use two radial basis functions for your neural network. So number of radial basis functions, that is activation functions, that we are going to use depends on the number of neurons in your hidden layer. So because we have two hidden neurons, we must use two radial basis functions for our problem. Okay, so once we identify this architecture, we can continue with the remaining things. The next thing is you need to define the corresponding radial basis functions for each hidden neuron separately. So phi1 of x is for the first hidden neuron, phi2 of x is for the second hidden neuron. Okay, so we'll define it with a general radial basis function. We know the formula for radial basis function, that is equals to e power minus norm x minus x1 whole square, and phi2 of x is equals to e power minus norm x minus x2 whole square. Assuming this x1 and x2 as centers defined like this 1 1 and 0 0. Okay, so you need to pick the centers that represents the same output value. So we know that 0 0 and 1 1 both represent an output class 0. Okay, therefore you should pick the centers as uh, the same class input patterns, or else you can go with 0 1 or 1 0 as I explained in previous class also. Okay, so this is our next thing, defining the radial basis functions for each hidden neuron that we define in our architecture. Because we have two hidden neurons, we define two things here, phi1 of x and phi2 of x. Each is defined for one center. So phi1 of x defines for x1 center, where x1 is 1 comma 1. Phi2 of x is defined for x2 center, where x2 is defined as 0 comma 0. Okay, right. So now our architecture is ready with the radial basis functions also. Now in our next step, what we will do is we will calculate the interpolation matrix. Okay, the interpolation matrix that will be used for converting our input space into hidden space. Okay, so we know what is an interpolation matrix. I explained this in the previous class, so please go through that video if you are not aware of what is interpolation matrix, or else you can simply see this formula. Interpolation matrix is phi ij, where this matrix is identified as a n by n matrix like this. So phi is equals to phi 1 1, phi 1 2, because we have two hidden neurons, and phi 2 1, phi 2 2, phi 3 1, phi 3 2, phi 4 1, phi 4 2. Okay. So how do you identify the size of this interpolation matrix? The size of interpolation matrix is going to be n by c. N by c. What is meant by n here? N is the number of input patterns. N is the number of input patterns. So how many input patterns are there? Uh, for XR problem, there are 4 input patterns given. Okay, 1 1, 1 0, 0 1, and 0 0. So n represents the number of input patterns, and c represents the number of centers. How many centers we put? So we pick here. There are 2 centers we picked. That is 1 1 and 0 0. So the size of this interpolation matrix is identified as n by c, where n is the number of input patterns given and c is the number of centers that we choose. Okay, therefore it becomes 4 rows. It's a 4 by 2 matrix now. Okay, so it's a 4 by 2 matrix because we have 4 input patterns. Okay, 4 rows and 2 columns. So 511, 512, 521, 522, 531, 532, 541, and 542. Okay, so this is how we identify the size of interpolation matrix. Now, let us calculate all the values of interpolation matrix. Okay, so 511 is equals to, the formula is, we have identified the formula as, let me show you the formula. The first formula is phi 1 of x is equals to e power minus norm x minus x1 whole square. Okay, so here 511, 521, 531, 541 will be for the first center, that is phi 1 of x. Okay, and 512, 522, 532, 542 is for the second center, that is phi 2 of x. That is, first center is 1 comma 1, second center is 0 comma 0. So you need to remember this entire thing, 511, 51, 521 and so on, will be for the first center, center 1. Okay, and the remaining 512, 522, 532, 542 and so on is for the second center. Okay, center 2. This is for center 2 and this is for center 1. Now what is the formula for this? E power minus norm, some points, 2 points are there. Okay, now let us identify the formula first. You should understand the formula. The formula is, suppose if you have e power minus norm 1 comma 1 minus 1 comma 1. Okay, it's going to be e power minus square root of 1 minus 1 whole square plus 1 minus 1 whole square, that is square root of 0 plus 0, and we have a square. Okay, square and square root will be cancelled. It becomes e power minus 0. We know the value of e power minus 0 is 1. Okay, and similarly for this, suppose if you have, assume that this is a comma b and c comma d, what will be the formula for this? The formula for this is going to be, norm of this formula is going to be square root of, let me write the formula clearly. Okay, assume that a comma b and c comma d are 2 points, then the formula is going to be a minus c whole square, okay, plus b minus d whole square. Okay, square root of a minus c whole square plus b minus d whole square, and we have a square for this entire thing. Okay, and before this we have minus. This is the formula. So as we all know, square root and square gets cancelled. So whatever value you get for this a minus c whole square plus b minus d whole square, along with a minus that comes as a e power value. Okay, so here for this, let us calculate the value 1 minus 1 whole square plus 0 minus 1 whole square. Okay, 1 minus 1 whole square is 0. 0 minus 1 whole square is going to be 1. Okay, and square root and square will be cancelled. It is minus of 1, therefore e power minus 1. So the value is e power minus 1. E power minus 1 means what will be the value for this e power minus 1? Just calculate it using your calculator. It is going to be 0.3678. Okay. Similarly, we will calculate 531. It is going to be the third input pattern. This is the third input pattern, and this is the first center. The meaning is from the third input pattern to the first center. That is the meaning. So this 3 represents third input pattern. This 1 represents the center 1. Everywhere the meaning is going to be same. 511 means from the first input pattern to the center 1. That is the meaning. And here it is from the second input pattern to the center 1. Okay. So we know that the third input pattern is 0, 1 and the center 1 is 1, 1. So the value is 0 minus 1 whole square plus 1 minus 1 whole square. That means it is going to be 1 square, that is 1, and we have e power minus 1. Okay, so this value is e power minus 1. It is same as the previous value. So it becomes 0.3678. You can verify the value with your calculator. Okay. Then 541 means, guess the 541, what it will be? From the input pattern 4 to the center 1. That is the meaning. Therefore, we have the fourth input pattern as 0, 0 minus the first center is 1, 1. 0, 0 minus 1, 1. The formula is going to be 0 minus 1 whole square plus 0 minus 1 whole square. It's going to be 2. So e power minus is already there. So e power minus 2, the value is 0.1353. Okay. So this is how we calculated 511, 521, 531 and 541. That forms your first column of interpolation matrix. Similarly, we can calculate the second column of interpolation matrix as 512, 522, 532, 542. What is the meaning of this now? 512 means that from the first input pattern, to the second center. What is our second center? It is 0, 0. So again, we start with first input pattern 1, 1. Okay. The centers are now going to be 0, 0. So calculate it. 1 minus 0 whole square plus 1 minus 0 whole square. So it's going to be e power minus 2 again, which is going to be 0.1353, which is similar to the previous value. Again, 522 means that from the second input pattern to the second center. So second input pattern is 1, 0 and the second center is 0, 0. The formula goes like this: 1 minus 0 whole square plus 0 minus 0 whole square. It's going to be 1 square, that is e power minus 1, which is 0.3678, which we calculated earlier. Okay. Then 532 means that from the third input pattern to the center 2. Okay. It's going to be third input pattern is 0, 1 minus center 2 is 0, 0. So it is 0 minus 0 whole square plus 1 minus 0 whole square. It is again going to be 1. We have a minus before that. So e power minus 1, it is 0.3678. Okay. Now, finally, the value for 542. What does 542 mean? It is from the fourth input pattern to the second center. Fourth input pattern is 0, 0. Second center is 0, 0. So 0 minus 0 whole square plus 0 minus 0 whole square, it is 0. So e power minus 0 is 1. Okay. So we got second column of values also for the interpolation matrix. Right. So if you understand this, the remaining things are going to be very easy. Okay, now let us represent this in the form of a matrix. The first column we got 511, 521, 531, 541. What are the values? 1, 0.3678, 0.3678, 0.1353. Okay, so these are the first column of values. And the second column of values is 0.1353, 0.3678, 0.3678, and 1. 0.1353, 0.3678, 0.3678, and 1. Okay, so this is the interpolation matrix. Now we need to add a bias value, a bias term to the interpolation matrix. So this column is added to the interpolation matrix as it represents the bias term. So you can add it anywhere as first column or third column. Whenever you add it as first column, then when you calculate the weight vector, the first value is assumed as the bias value. You can add this once as third column also, then the third value in the weight vector will become bias value. So based on where you add, the corresponding weight vector gets the bias value in the corresponding position. So since we added these ones as first column, we get the bias value in weight vector as first value. Okay. So after adding this bias term 1 as first column, calculate the transpose of this uh, interpolation matrix now. Phi t. This will be of size 3 by 4 now because we got 4 by 3. Now it's going to be 3 by 4 matrix, which is simply a transpose of this. Okay, every row becomes column. So first row becomes first column, second row becomes second column, and so on. Third row becomes third column, fourth row becomes fourth column, and so on. Okay, so once you got this, we are now ready to calculate the weight vector that identifies our RBF neural network. Okay, so how do we calculate this weight vector? As we know, the formula for weight vector, as I explained in the previous class, W is equals to phi into D. So that is the formula we identified in our previous class. So it's going to be now the inverse interpolation need to be performed in order to identify the value of this weight vector. Okay, because uh, there may be uh, the unequal sizes between the vectors that we are going to multiply. Therefore, to uh, make those sizes, vector sizes uniformly so that we can perform the multiplication, we need to perform this inverse interpolation on the corresponding interpolation matrix. So how it is done, please remember this formula. The formula for inverse interpolation is going to be phi power t, that is the transpose of phi, we already calculated this, into phi, this matrix, whole inverse, we need to consider that whole inverse, into phi power t again. So this will perform the inverse interpolation, and that will become the phi, okay, into the desired output t. Okay, so if we calculate this, then we get a weight vector W that defines our radial basis function neural network. Okay, now let us calculate these values one by one. We will start with phi power t into phi first. Okay, phi power t into phi. Okay, this is not clear. Phi power t into phi. We are calculating this now. So this is phi power t, 3 by 4, and this is phi, which is 4 by 3. So we can multiply these two matrices as the number of columns in the first matrix is same as number of rows in the second matrix. So after performing the multiplication, we get this matrix. Okay, it's a simple mathematics matrix multiplication. You can perform it in your own. You can verify the answer like this, right? So once you get phi power t into phi, the next thing is what is the size of this matrix? The size of this matrix is a 3 by 3 matrix, because we need to find out the inverse of this matrix. It should be a square matrix. Okay, so we got a square matrix. That is what we did. To find this 5 power t into 5, we'll convert the matrix into a square matrix. Okay, otherwise we cannot find the inverse, right? So now it is 5 power t into 5 is calculated. Now the next thing is we need to find out the inverse of this matrix. 5 power t into 5 whole inverse. So you can calculate it manually, or just use your calculator to identify this inverse of a matrix, square matrix. So you should get these values: 5.7274 minus 5.8553 minus 5.8553, 5.8553, 6.9281, 5.5907, minus 5.8553, 5.5907, and 6.9281. So please clarify this answer. You can go manually also. You can calculate it manually. I think you know how to calculate the inverse of a square matrix. It's a simple mathematical formula. Anyhow, I'll just tell you how to calculate it. The first value will be 4 into this value into this matrix, D minus B minus C, the corresponding diagonal. You need to consider this D minus B minus C minus A and this one. Okay. Similarly, when you consider this 1.8709, you need to put these 1.8709, 1.8709, 1.4058, 1.2888 as ABCD, and take it as D minus B minus C A. Okay, and so on like that. I think all of you know how to calculate the inverse of a 3 by 3 matrix, or else just go through some mathematics to identify that. Okay, so somehow you will be calculating this inverse. I'm not explaining how to calculate the inverse now. Okay, so now once you get this inverse of 5 power t into 5, okay, now you are ready to multiply it with 5 power t again, and also into desired response. Okay, so we got this value for 5 power t into 5 inverse. This is the matrix, and the matrix size is 3 by 3. We got this as 3 by 3, and then this is 5 power t. We got this as 3 by 4, 3 rows and 4 columns. And the desired response, that is the output vector, we know it as 0 1 1 0 for the XR function from your that is XR definition. Okay, so this is the size of this is going to be 4 by 1. Okay, so now there are 3 matrices, 3 by 3 into 3 by 4 into 4 by 1. So either you can start multiplying these 2 matrices, because the number of columns in the first matrix is same as number of rows in the second matrix. Then you will get 3 by 4 matrix, and then you can multiply it with this 3 by 4 and 4 by 1. So finally you will get a matrix 3 by 1. Okay, so after performing these multiplications, you should get these values: 2.8404 minus 2.5019 minus 2.5019. Okay, so as I explained, because we took all the biases once as first column of the corresponding interpolation matrix, you should consider that first value as bias. Okay, if you kept that once as third column in the interpolation matrix, then you will be getting the bias value here. Okay, anyhow we took it as first column, so the first value is considered as bias value, and the remaining two are weights, W1 and W2. Okay, here we got the same bias values, 2.50919 and 2.509. Okay, so now once we identified these, the neural network architecture now becomes W1 is equals to minus 2.5019, W2 is equals to minus 2.5019, and a bias is connected to the output neuron as 2.8404. You may get a doubt here about what is about the weights over here. You don't require any weights for converting the input spaces into hidden space, as we are using a nonlinear mapping here. So we don't use any weights here. The phi function, the function phi, that is interpolation matrix, is used here for converting your input space into hidden space. Okay, and once you get that, the linear mapping needs these weights. Okay, nonlinear mapping does not require any weights. Linear mapping requires weights. Therefore, we are using weights over here. Okay, so this will be the final architecture of our neural network, and we can say our RBF neural network is ready to predict the outputs for any given input. Okay, let us check whether the RBF neural network that we designed here is working properly or not with the help of a sample testing here. Okay, so let us verify the answer by considering the input pattern 1 0. Okay, so we know that for the input pattern 1 0, the output that should be produced is 1. Okay, 1 0 should produce output as 1. Okay, so this is the architecture we got. Okay, for nonlinear mapping, we will make use of phi, the interpolation matrix, and from here to here, we will make use of W1 and W2. Okay, so let us say phi 1 into W1, this is what we do, plus phi 2 into W2, plus there is a bias. This will be our formula for calculating the final output of our radial basis function neural network. So f of x is equals to phi 1 into W1 plus phi 2 into W2 plus bias. Okay, so phi 1 means the distance between the first center. Okay, the first center and the input pattern. So what is the input pattern we considered? It is 1 0. Okay, and what is the first center we assume? It is 1 comma 1. Okay, therefore e power minus norm 1 0 minus 1 1 whole square. So this is phi 1 into what is our W1? It is minus 2.5019 plus phi 2. Phi 2 means that the distance from the input pattern to the second center. Okay, so this is center 1 and this is center 2. Phi 2 always represents the distance between center 2 and input pattern. So phi 2 represents the distance from input pattern to center 2. So it is going to be e power minus norm 1 0 minus 0 0 whole square into W2. What is W2? It is minus 2.5019. And finally, plus 2.8404, which is going to be the bias value. Okay, so if you calculate this, you will get 0.3678 into minus 2.5019 plus 0.3678 into minus 2.5019 plus 2.8404, which will be finally evaluated as 1.5 zeros followed by some ignorable value. We can say that this is approximately equal to 1. Okay, so the desired response for this input pattern is 1, which, and our radial basis function neural network also calculated the expected output, that is output as 1. So it is working fine. The radial basis function neural network is working fine. You can also test for some other input pattern. Try to calculate it for 0 comma 1 or 0 comma 0. For 0 comma 1, the output should be 1. For 0 comma 0, the output should be 0. For 1 comma 1, the output should be 0. You can test for other input patterns also. Okay, so you please practice one more input pattern and verify its answer, right? So with this, we have completed the design of RBF neural network also. Okay, I hope you understood this concept of designing the RBF neural network. Let me conclude the things we discussed today briefly. We started with the architecture of a radial basis function neural network, uh, which consists of one input layer, one hidden layer, and one output layer with exactly one neuron. And the nonlinear mapping is performed between input space to hidden space, and the hidden space can be transformed into output by using a linear transformation. Okay, so uh, for nonlinear mapping, we will make use of radial basis functions support. That is, we construct an interpolation matrix, and then we convert the input space low dimension into high dimension space. Okay, so once we get it in high dimension space, then we can convert into the output space. Okay, and then we have seen how to design a RBF neural network for a simple example, that is, we considered XR gate functionality, and then we designed it with the help of few steps. We started with assuming an RBF neural network architecture for the problem, and then we uh, calculated the interpolation matrix and performed inverse interpolation to identify the weight vector of the RBF neural network. And finally, we tested whether our RBF neural network is working properly for the given input patterns or not. Okay, so I hope you understood this problem. Please practice the design of RBF neural network. It is very important in examination point of view also. Okay, so that's all for today. Thank you all for your patient listening. We continue the topic in next session. We'll discuss where we discuss the training algorithm for RBF neural network. Okay. Thank you all once again.